difficult. Okay.
Mechanical printer view.
Yes. Kinetic one. Okay, I suggest we start. So, Erwan will talk today, and I'm afraid I'll need to leave in the middle of the talk. So, Carolina Rassel will take over for questions, and if she's not there, then Elena is the boss, as always. Please.
Okay, thank you, Arié. So what I will present, in fact, will concern essentially the wave equation in higher dimension, nonlinear. So this is a joint work done with Joachim Bernier and Benoît Coudet. So Joachim is a young student of me and Nicolas Crouzet. So I will present you the results, then discuss the proof, then talk about the technique of the proof, and then show you some relaxing numerical experiments. Okay, so the equation I'm looking at is the wave equation, linear. You add an m, and you add a nonlinearity, f of u, which you might think to be u squared, u3, u to the 4. Polynomial, and with a 0, or at least 2 in 0. I assume periodic boundary conditions, and the dimension plays a role. So I will consider small epsilon, of size epsilon, small initial data, and smooth in the sense that the space will be hs times hs minus 1, which corresponds to the standard space for solving the wave equation for the u and the time derivative of u. And so in the end of the 90s, there was this result by Bourgain, in fact, and Dario. Dario first and Bourgain, and IDs were already present in some previous work of Bourgain, but it was concerning the nonlinear Schrödinger equation. So you can have almost global existence. So of course, if you are on RD, then and if you not in this case, but if you are, I mean, you have no dispersion in this equation. So it's hard to obtain a global existence result. But what you can prove is that if you start small, you will remain small for a time that is so here epsilon to the minus r but r is fixed and all the constants depend on r. And if you optimize then R with respect to S, and if you assume analyticity, you obtain typically an exponentially long time, like Negoroshev estimates in the world of dynamical systems. So, so the result of this result says that it holds true. Of course, if you have no nonlinearity, it is true for all time. Huh? So the Sobolev norm is completely bounded. But if you add the nonlinearity, then the same holds true, but for almost all n. Which means that you have a kind of UQ problem. For almost all m, you have preservation of the Sobolev norms. And it holds only in the case of the dimension 1. I will try to explain you why. So it was first proved rigorously by Dario, but for periodic boundary conditions. And then for Dirichlet boundary conditions, and then for periodic, because you have a multiplicity problem, it was proved in a general framework by Bambouzi and Gray. In dimension 2, open question. In dimension 2, it was an open question. I mean, this is still an open question to prove this, you have some result, but essentially the air here is restricted. You cannot take air as large as you want because it is restricted by F, but you can have result by the law. So what we prove with on a Sobolev, but assuming the initial data is much more regular than the norm you want to control. It is exactly, in fact, the idea comes from numerical analysis. So it's, if you write a convergence proof, you have control in L2 if you assume that the exact solution is in H1 or H2. And the idea comes back to the thesis of Guillaume Dujardin. We try to explain. You have it means that you will not require a global control of all the HS norm, but a control of the HS norm of the high modes and the L2 norm of the low, the HS norm of the low modes and the L2 norm of the high modes. And then after that, you make you play with the scaling and you obtain such a result. Okay, so this is our result, and it also introduced a new technique to deal with more resonance situations, because so if m equals 0, it is a resonance situation. The spectrum is made of integers, of integers in the one-dimensional case. It's not a square root of integers for the multi-dimensional case. But if m equals if m equals 0, then we have resonance of the linear dynamics. So what did I want to say? Okay. Okay. So now, I mean, so this kind of techniques allowed us to control the situation. Okay. Yes. What I want to say is that if m is different from 0, in dimension 1 you are very non-resonant, and in dimension 2 you are less non-resonant. So dimension 2 is between the case m equals 0 and the dimension 1. You can say, and numerical schemes will be in between. Okay, so now so this technique allowed us to improve some known results for the long-time analysis of numerical schemes. So the typical scheme you will use to implement the nonlinear wave equation is a highly oscillatory integrator. In fact, you can probably more or less prove that every scheme standard reduced to this kind of scheme upon a slight change of the linear frequencies. So omega is this operator minus Laplace plus m square root. So these are the frequency of the wave equation. And the wave equation in dimension 1, it is k. It is like k plus something. And so if you imagine that here omega is 0, you will end up with the Verlet method. But the family of highly oscillatory integrators have this form. And the one of the first one was if you take psi equals the sinus x over x, and phi equals 1, and then it corresponds to a splitting method. So it's just a splitting method between the linear and the nonlinear part, written in the wave framework. Okay, but you have many other methods that were developed. Phi and psi, they are filter functions. And this can be very easily implemented if you can compute the exponential of, which means the cosinus. So the cosinus or the exponential of h omega, so it requires either some Longchamp type method or Fourier. And of course, if in the case of periodic boundary condition, you can easily implement this scheme in Fourier. So here, for example, you go into Fourier to calculate the multiplication by, to compute the multiplication by phi, then f. You go back to the x variable and then Fourier again. And the symplecticity condition means that you have this relation between the two filter functions, and this it corresponds to a splitting method with a filtered nonlinearity. So the analysis of this scheme was done so the first result is, so now the long time behavior of such one was available from the analytical point of view. And if you take a symplectic method, then you have a stability in HS uniformly in K. K is a number of nodes, number of points in your, on your grid, but you needed a CFL condition. Of wave type, of course. And the bad news is that the constants of the CFL here depend on R, R being the time horizon, so epsilon to the minus R. Okay, then using normal forms with Eric Paturel and Benoît Gréber, we establish something complementary in some sense. So either you change the restriction on H, you change to a restriction on epsilon. So CFL on epsilon, but with an alpha, of course, depending on R. But now it does not hold for all H, but for almost all H. So you can have resonances for very specific time steps. So and in fact, you can indeed construct example for the Schrödinger equation where you start in H1 with a small numerical solution, and at some point of course you cannot go to infinity, you know, because the H1 norm is dominated by the L2 norm, and the L2 norm is an invariant. So but K is it measures the embedding in H1 into L2 in a set of sequences. Huh? So you cannot blow up, but you can reach epsilon to the K, which is the upper bound of the H1 norm. So you can really see that there exists some resonant time steps. Okay, and the other result that we had was that if you truncate, so it's like a cutoff in frequency, like you did in Vlasov with Lucas. So if at each step you throw out the high frequency, some part of the high frequency. So if you cut the high frequency, you can prove that if you cut it at the right level, then you will have this preservation. But it's a non-symplectic, and you have to essentially know everything about what you want to prove. So it's not okay. So using this technique, what we prove is the following. So in dimension 1, greater than 1 now, so we obtain the same thing that we had at the continuous level. So if you of course, you have a loss of derivative here, but you have a control for an arbitrarily long time. And you have so you have a combination of a CFL condition and a CFL on epsilon. So then the result is for almost all M, so the mass parameter in the wave equation. And then for almost all H, you have the result. But you can always find a resonant H, a resonant M. Okay. So if you take beta equals 1/2, if you take beta equals 1/2, so you have essentially no condition on epsilon, and you have changed here the CFL to K 1/2 instead of K. So you have reduced the CFL, and if you take beta equals 1, you have no condition on H0, but you have here a condition that does not depend on R. And it's the same here. If you take beta equals 1/2, this does not depend on R. So now I will talk about how it works, so a bit of techniques, and then I will show you that you might think that there is an easy way to avoid this kind of time resonances by paying the price. So you take implicit integrators and it will work, but in fact it is always there. The only way to avoid this problem, so for almost all H, is to take a CFL, even for implicit schemes. I will show you. So this is really a bad news, I think, for the moment. I do not know any scheme that avoids the CFL. I will show you many different examples. You will see. it's still an open. But okay, almost all, in many situations, you will have an idea of what is this set. Okay, so how does it work? What is the general strategy and where does it come from? So here, this is a Hamiltonian formulation of the wave equation. So here, for the beginning, I've done nothing. Omega square, this is just this operator. And I introduce the symplectic variables Q and P. So you push here and you push there. And you end up with such a system. Q dot equals omega P, P dot equals minus omega Q. I've done these computations probably, I don't know, 100 times in my life, because always there is a square root of 2 missing or something like that.
So you don't factor Laplacian as discret, you factor the square root of Laplacian, square root of Laplacian.
The square root of the Laplace? What do you mean?
So the omega, these are not differential operators, right?
Yes, it's a differential operator. But positive.
So wouldn't the usual way to write that as a Hamiltonian system factor Laplacian as a divergent gradient? That would be.
No, I don't think so. I don't think it's related. No. If you write it as a divergence of a gradient, you have to take the square root of this divagrad operator. You have to take the square root of this.
How do you implement these pseudo-differential operators? How do you implement omega?
Fourier, yes. Fourier, or you have to take a way to implement the exponential, the cosinus of this matrix. So exponential of this matrix.
So you can do it in a periodic setting, but
so either you do in a periodic setting. If you do on a domain, then you have to find a way to compute the exponential. So, but usually it's sparse, and then it's not measurable. But you have technique Long-Shaw's to compute the exponential. This you use as a black box, certainly. For me, you use Fourier.
So if m is equal to 0, you don't have ddx.
If m equals to 0,
This square root.
it is
In 1D.
this operator,
All right.
which is a symbol in Fourier. So either you are in Fourier, so the symbol is just psi, or you are on a domain with some boundary conditions, and you have to interpret this as the multiplication by lambda j, or the square root of lambda j, where lambda j's are the eigenvalue. So in the orthogonal basis, and typically this lambda j always behaves like j square, asymptotically for large j.
How large is m?
0, 1. No, not 0, 1. 1, 2. 1, 1, 2. In fact, it's for almost all m, the result. But when you have fixed an m, then every constant depends on m. Okay, so I have this Hamiltonian formulation, and then when you see such a system, you take this complexification of the system, and you end up with a Schrödinger version of the wave equation, where omega is essentially this operator. So this is the wave equation. And the nonlinearity now. So here this is the Hamiltonian associated with the nonlinear part. So if you write it in complex formulation, it gives you this nonlinearity. So it's like the Schrödinger equation, except that instead of having psi square multiplied by psi, you have something like regularization here in the nonlinearity, but will not give you any. Okay, so now the linear flow. First, you have to understand the linear flow. If you look at the linear flow in Fourier now, so Fourier here is important. If you are not in Fourier, you have to deal with this, and you have to know everything about the eigenfunctions of the Laplace. But in Fourier, these are exponentials. If you work with a harmonic oscillator, it will give you another type of basis. But you decompose here in Fourier the solution, and this linear wave equation is equivalent to this collection of equations for the complex numbers psi k with these oscillations. And of course, you can write down explicitly the solution, and you see that the moduli of the Fourier coefficient is constant along the flow. So it's just a superposition of harmonic oscillators that do not interact. And this preserves the HS norm, because if you look at the HS norm in Fourier, it is essentially driven by the sum of the Fourier coefficients, and this does not move. So the HS norm is preserved, because all the IK. So from the dynamical system point of view, you can say that the original unperturbed Hamiltonian is the sum of integrable Hamiltonian IK that commute and that commute, and that are 1D, so in the sense, so it's a completely integrable system. So now the persistence of the stability of such a system relates to questions of nonlinear stability of integrable systems. So this goes back to Poincaré, Birkhoff, and so on, KM theory. But here in an infinite dimensional setting. So how do we do? What is the general goal? The general goal is a nonlinear diagonalization. If you want to know the behavior of a linear system, y dot equals a y or I a y. If you want to know the behavior of this system, you diagonalize it. Okay, so you remove the off diagonal term, and then you can write down explicitly the solution. Here it's more or less the same. If you write the Fourier coefficients psi k, you write them as the square root of ik, that I call the action, and a phase. If you look at the Hamiltonian, so the Hamiltonian is something like that. So it's probably not written exactly, but it is the integral of this with respect to psi bar. So it is f of this function. And you put the Fourier expansion, and then you look at what it gives. And it gives a polynomial, p, in an infinite number of variables. And depending on psi and psi bar. It's a terrible object. But once you have the summation, once the coefficient decay, you can sum this. And if you write down here in terms of these variables, you see that you have the square root of I, and here sum and differences of angles. So imagine that you have only one angle here, one angle here. It will correspond to a quadratic Hamiltonian. So we are exactly in this situation. And what you want to do is to remove in the Hamiltonian the term that depends on theta k1 minus theta l1 with k1 different from l1. And you want to do for all the terms that are nonlinear. And if you remove, so if you make a transformation, so for the matrices, transformation is just a linear transformation, but for nonlinear systems it's more complicated. Then you end up with something that do not depend on the angles and depend only on the actions. And when you have, if you have found a symplectic transformation such that you depend only on the actions, and then you will have preservation of the HS norm. And of course, you will be able to do this up to some small remainder term. And what you can say is that after r iteration of the process, you can push this remainder to an arbitrary order. Okay. Okay, so now this is the strategy. You want to find a symplectic transformation such that which is close to the identity. So which means that if psi is small of order epsilon, the perturbation is of order epsilon squared. And in the new variables, of course, it's symplectic, so you just need to look at the Hamiltonian. It is the sum of an integrable Hamiltonian here, depending only on the action, so a diagonal one, if you prefer, and something that is small, if psi is small. And now you do the commutative diagram, so you make the change of variable. You start with psi 0 small in HS. Well, by this estimate, it implies that W is also small in HS. W evolves according to this system. So it means that all the ik, because they will commute with the first part here, and so that will be 0. So you can see that the moduli of the Fourier coefficient is evolved like this. So it means that for t is smaller than epsilon minus r, psi is smaller than epsilon s in Sobolev, and then you go back. This is really what you will do if you want to have information on this dynamical system. Except that here you will have some. And much more than that, you see that this moduli, so the actions, the moduli of the Fourier coefficient, they evolve, so they really do not move at the initial scale. So if you start with an analytic data, for example, you have a certain decay, and you do not move at this decay. I will show you in the numerical example. This is exactly what you have. Okay, so now you do some algebra. You seek the flow, you seek the transformation under the flow of a polynomial Hamiltonian of the same form. You expand the flow, so this is the transformation you want to construct. You expand the flow. So this is, it starts with the identity, then a Poisson bracket between h0 chi and p chi, and something that is of order 4. And you end up with solving this kind of equation, which is called a homological equation. You want to inverse this. If you write this at the level of matrices, what I'm doing here, it's smart to do that. Yes. The level of matrices, I have something like that. So this is diagonal, okay. I want to diagonalize it. So I know everybody is symmetric. So what I do is I just do this. And I expand in epsilon. And if I expand the epsilon, I find d plus epsilon v. And so this should be equal to d plus epsilon d1 plus epsilon d. And this, if I expand this, I use some formula standard. And the next term is epsilon, and then you will have the commutator of S and D. Absolutely not, S and D. And there is probably a minus I. Correct? So the equation to solve, n plus O of epsilon squared. So the equation to solve from the matrix point of view is ds equals to 1 over I times b plus d1. And so now, if you write down d is diagonal. So if you write down this component twice, you will have lambda k minus lambda l multiplied by skl equals to something dkl minus Kronecker kl So if lambda k is different from lambda L, then you can solve. If lambda k equals lambda L, you can. So if lambda k minus lambda L, if lambda k equals lambda L implies k equals L, then I put it in the diagonal. This is the diagonal fit. But if you have k and L such that lambda k and lambda L are the same, you have a resonance and you cannot compute. If you want to do this, so to diagonalize with respect to one parameter epsilon, you have to invoke Cato, saying that you have a matrix that depends on a smooth parameter. And when you have eigenvalue crossings, the Cato's proof is absolutely, it's a love killer. Huh? At some point, it's absolutely not constructive. At some point, you say, it should blow up, it does not, so there is the solution. Yeah, so I don't want to enter into this question. Yeah, of course. But here, so I'm going to show you what plays the role of this lambda k minus lambda L in the nonlinear setting. So I want to identify, and so now, because it's nonlinear, instead of controlling omega k1 minus omega k1, I have to control something like that. Because if you calculate the evolution of the Poisson bracket with respect to the diagonal flow, so the linear one, then you obtain such a formula. So the solution will be under this form. So now you see it's not only a question of dimension. Of course, there is this question of multiplicity more than dimension. If you have multiple eigenvalues in this case, it's complicated, but you can answer. You can do clusters of eigenvalues. But here you see that it's even worse because you have a nonlinear relations. And the standard way to do this is to assume a Diophantine assumption, and here the business starts. So I will just shortly explain the technical point here. So here essentially it controls, probably in your language, it controls the gap between the almost crossings. Exactly this. So you will say that if you take K1, Km, L1, Ls, if you take such a difference, sum and difference like this, you control by gamma is a constant, and mu3 of KL means the third largest integer amongst all of these. So this is absolutely non-trivial because you will have two integers among them, say K1 and L1, who can be arbitrary. So this Diophantine assumption was identified by Bourgain, I think and Dario in the end of the 90s. I can explain you quickly why it works. Imagine that you make a truncation in n. N is a frequency truncation, and you collect in your Hamiltonian system, which is polynomial, the term linear, bilinear, and cubic, at least cubic in the high frequencies. And in fact, you can neglect the cubic term. Because for high modes, if you are nonlinear, you are very small. It's a tame property. Okay, so you need only to solve someone with two large integers. But if you now have two large integers, then you control the denominators by something like that, n over alpha. Because you have too high, the capital one, and the rest is small. And then you play with the numerology, and then you can end up with something. So now I will explain you why it's okay in 1D, why it's not okay in 2D. In 1D, you can, for large k, you have such a relation, okay? Now, by standard, it's relatively standard, because of the square roots, the derivative of this with respect to m is large. So you will not have, if you have an exact resonance, you just play with m and you are far away from the from this resonance. So you can prove that generically in M, this is relatively standard. Then, if you add the two terms like this, you will also have this because these terms are positive, it's not the problem. But you might have that here you have the two largest have the opposite sign. Okay. But then it's okay because in 1D, A and B are integers. So you can avoid integers, it's no problem. But in 2D, there are several ways to become large. In 2D, imagine that you have a first integer, so a first element of Z2 that is n and m and here n. Now, if you do the differences between two eigenvalues of the wave operator, and you expand, you have the n cancelling, and here you end up with n over m over n. So it's that. So the eigenvalue of the wave operator, the difference of two eigenvalues, so exactly like this, is dense. So there is no hope to have a control by the third one. Okay, so now I will not go more into details, but what the thing is that in this kind of diagonalization or normal form, when you cannot solve a problem, you do not solve it. You just write what you obtain. And what you obtain is that you cannot solve for these terms here who are quadratic in Y. And so instead of ending with someone preserving the HS norm, you will have two equations, one for the low mode and one for the high mode. And now the thing is that this preserves the L2 norm. So you preserve the L2 norm of the high modes and the HS norm of the low modes, and then you play. And you end up with something. Okay, so now I will talk about numerical schemes. So this is something. So if you want to understand the behavior of numerical schemes applied to this setting, the first thing is, okay, let's take the good case, so the dimension 1 case. Imagine that you have this. And now, believe me, if you do the algebra, if you work with time discrete operators, instead of inverting these small divisors, you have to invert these small divisors. Exponential of I, h, omega k1, so the same as in the continuous case, minus 1. It's like this. It's known in symplectic map, it is called by Moser. Symplectic map, if you want to play with symplectic map, if you want to do KEM with symplectic map, so instead of doing standard theory, then you end up with such a condition. So you see that now you are into trouble, because it's not only that you want to avoid this guy to be 0, but it is this guy, h times this guy, to be close to a multiple of 2 pi. So you can find h such that you will have here a cancellation. Not because this term vanishes, but because this term is equal to 2 pi over h. Okay. So without a CFL, you will never obtain something like that. So, but if you have a CFL, of course, then you use some kind of thing like that. If this thing here in the exponential is smaller than pi over 2, then you can control this by x, and then you can use the continuous condition. So if you have a CFL, it's okay. If you don't have a CFL, the generic conditions for h is not by mu3, but by mu1. And so we are back in the case of the wave 2D. In the wave 2D, we didn't have mu3, we had mu1. Okay, so that explains why we can obtain the result, but we cannot completely get rid of the CFL. We still can find problems where so you can still find here terms that even with a weak CFL that can cancel this. Okay, so it's a bit technical, but that's the way it works. Okay, so now I'm going to show you some examples and try to explain them. So I will not show you examples on the wave equation. I will show you examples on Schrödinger equation. So for the Schrödinger equation, it's basically essentially the same kind of techniques. But to play square root is very nice because you need only one parameter to have high derivatives. For the case of Schrödinger, the eigenvalues here are k square. And I will add a convolution potential here. So it's just for numerical experiments. So I perturb the omega k like this, arbitrarily, or you can put some random numbers, it doesn't matter. So this mimic, in fact, minus Laplace plus v, a smooth potential that you have diagonalized, and then in the good basis, you have this kind of eigenvalue. So it's not, it's to avoid exact resonances for a moment. I want to avoid exact resonances. And I take this smoothest possible initial value. And so if I use the splitting method outside the CFL, I obtain something like this. So here I take H, which is exactly, it's the opposite, I'm sorry. It's the opposite. So of course, this is in the non-resonant situation. So this is for H equals this term. And what you observe here is are the Fourier coefficients in logarithmic norm. So the log of these Fourier coefficients. And because the solution is completely analytic, this solution is the most analytic function with a pole you can imagine. And so you have a decay, an arithmetic decay, and you see that they oscillate at their own scale. So this is exactly the type of results that we had. So the modes do not exchange energy, but at the regularity level where they are. But if you now take this time step very close to this one, then you end up with something like this. So resolution is relatively poor. So you see that you have absolutely, so the result does not hold, and it is because now this creates a resonance in the analysis. Okay. But so when you show this to people usually one reaction is yeah, but you should do implicit schemes. It's stabilized. So I will use implicit explicit integrators, which means that I will do splitting, as you would usually do, between this linear and this nonlinear part. And I will approximate the linear part by the midpoint rule instead of the exact splitting. So in Fourier, of course, it's easy to do, but if not, you have to invert the matrix. Okay, so R is this rational function, which is the stability function of the midpoint rule, and phi here is the exact flow of this part. So for the Schrödinger equation, it can be integrated exactly, because the modulus of u along this flow is constant. So you have a IMEX scheme, as it is called. Okay, so I have to cook up some specific initial data to produce good pictures. So let me take this one, so my favorite analytic function, plus 3 modes. Okay, 3 modes like this. Small. So now I use some. I do not use such a huge number of grid points, but this is typically what you can observe for the exact solution. So everybody oscillates without any energy exchange. And now you use the implicit explicit integrator. You see, you take here a time step that is very close. Sorry, this is for implicit explicit integrator, and this is for 0.13, and this is for 1.12. But this H is such that you have this relation. And this relation comes, why do you have a resonance for this? It's because when you do There is no way to erase. Okay. The formula is just 1 plus ix divided 1 minus ix. So it means that when you implement the midpoint rule, it is like doing an exact integration of a modified flow with work tangent. And so now, if you want to analyze the long-time behavior of the flow, you will have to make sum and differences of arc tangent, and you can find h such that you have this strange relation here that makes that you have a very bad behavior of the implicit explicit. But you can say, okay, implicit, explicit, there is still the word explicit. Come on, do midpoint rule. And if you do the midpoint rule, so the midpoint rule first, it can be more or less expressed also as a splitting method between so with an implicit, with the linear part treated implicitly, and something, if you expand this, something that is the flow, a modified flow. So the implicit rule is more or less a splitting scheme. And if you take the same parameters, you will not observe such a dramatic blow-up, but still this is the exact solution, and just very close to it, you have energy exchanges between the modes, and they are not physical. They are not. Okay. So now you do the opposite. Imagine that in the system I give you, I have resonances, physical resonances. That's life. Sometimes it happens. And so here I tune. I will show you another example later. I tune especially omega 2, omega 5, omega minus 7 to satisfy this relation. The exact solution now, computed with splitting linear, exhibit energy exchanges. So you have, so you see here you have very high modes, and they exchange a lot. So you have energy, non-linear exchanges between with the energy. Okay, and now this is the implicit explicit integrator, but it has completely killed the energy exchanges. And why? Because now if you take this h, you calculate arc tangent, this is 1/2, and now this small denominator with the exponential should be 0 to reproduce the energy exchange, and it is not 0, so in fact you can average. So the implicit integrator has broken the physical resonances. And this is the same by the midpoint rule. So I will give you here a more specific, more physical example if you want. So if you take now the nonlinear Schrödinger equation, resonant one, in T2, so the torus, and if you take this initial data made of 5 modes, sorry, mode 0 plus 1 minus 1 plus 1 minus 1 in two directions, then we can prove that there exist energy cascades. And this was proved by Rennes and myself, that so you do not have the preservation of the you have energy exchanges between the modes and a time scale that depend on that it evolves like a cascade. And essentially it's because if you have such a relation like this, then the 4 modes form a rectangle in the resonant modules. And this is typically what you will observe for the exact solution. So in logarithmic scale, so you start with some modes here, and they excite some higher modes. Okay, they excite some higher modes, and this higher modes grows to come to something that is very large and very significant. Okay, so in fact, on T2, there are many open questions. In particular, can we find examples that are called turbulent, so more or less like this, where you have a Sobolev norm growing to infinity? This is still an open question asked by Bourgain, actually. Okay, so this is the exact solution. Now, so you see, I refined completely the schema to have a CFL 0.1. So I'm sure that this is correct. Now I use an explicit scheme, but outside the CFL regime, or very close to the CFL limit given by the theorem. And you see, okay, some energy exchange that look pretty close to the exact solution. be discussed. But, okay. And now you use implicit integrators, and you see that you have no energy cascade. Because you have completely changed the eigenvalue. You have, okay, maybe you have smoothed the integrator, you have killed the high frequency, but you also have distracted completely the resonance effect. Okay, so I think I will stop here, and thank you for your attention.
So now I'm Ariel. Ask for questions. Please.
No, sorry.
No,
Questions? Yeah?
Can you reveal the size of S star in your theorem?
Yes, S cube.
Ah, it's S cube, not so bad. Not so bad. I expected more.
It's S cube. It's finite. No, but that's important. So probably if you work with analytic functions, if you optimize correctly, you will change rho to the analytic bound to rho divided by 2. And all the function will depend on rho. But no, it's S cube or maybe S5 now. I'm starting to think. S cube was, you know, the first.
The first try.
Come, our shop is open.
Could you do better with completely integrable discretizations?
But in this case, it is not completely integrable. I mean, of course, for NLS, yes. For nonlinear Schrödinger equation in 1D,
Is there this Ablovitz
if you have Ablovitz-Ladik, then no problem. You will find. Of course, you will still have this problem if you implement it with if you implement Ablovitz-Ladik with a splitting algorithm, you will have the same problem. But if you implement it with a midpoint rule, I don't know, but probably no, you should have the same sort of problem. But, because when you play with the time integrator, but I'm sure that you can find some symplectic. I'm sure you can find some specific symplectic integrators, time integrators for Ablovitz-Ladik, because you have an action angle variable. It's in the book of Erwan and Lubisch, I think. No. But okay, but in general, it's not integrable. No, what you maybe the only question would be, and this I erased this part. To modify the nonlinearity. To modify the nonlinearity, but you would have to include the small denominators in Fourier, and this is non-diagonal, so it costs you a lot. So you know this game that you want to cheat with the nonlinearity so that it averages better. But the natural way is to cheat in Fourier, and if you want to have a quadratic nonlinearity in Fourier, it costs you n to the square instead of n log n. That's a very fun game.
I have another question, still concerning the m. M equals 0 should be very difficult, right?
Yes.
Because then your omega is very bad. But it's somehow not reflected in your results, right?
M equals 0?
Yeah.
In almost all, I avoid 0 in the bad set.
That's cheating, right?
No, that's not cheating. No, in fact, yeah, no, the result is for almost all in the fixed interval. I don't know if it's written somewhere, but I'm sure it is.
Yeah, for almost all m positive.
Yes, almost all m positive.
And how does it come to be an almost an all statement? I mean, what you showed doesn't
So which for this one?
Yeah.
It's because you want to satisfy this kind of relation. This kind of relation.
Ah, it's really a Diophantine game.
And it's of n, depending on k. So you calculate all the derivative of m, which depend on all the collection of k. And you prove that the size of the, in fact you prove that the size of the ball, so all the m satisfying the inverse inequality, you can sum, because here you have a decay.
Yeah.
You can sum, and then obtain gamma, the set of size gamma, and for all gamma, and then the moral quantity. No, it's just another question are for waterways, for example, this is not true. So I said things are starting to change. You have many new results in this direction.
So let's thank Erwan again.
Thank you.